This field is all about codifying the idea of symmetry. For example, when we say a face is symmetric, what we mean is that you can reflect it about a line, and it's left looking completely the same. It's a statement about an action that you can take. Something like a snowflake is also symmetric, but in more ways. You can rotate it 60 degrees or 120 degrees, you can flip it along various different axes, and all these actions leave it looking the same. A collection of all of the actions like this taken together is called a group. Kind of, at least. Groups are typically defined a little more abstractly than this, but we'll get to that later. Take note, the fact that mathematicians have co-opted such an otherwise generic word for this seemingly specific kind of collection should give you some sense of how fundamental they find it. Also take note, we always consider the action of doing nothing to be part of the group. So if we include that do-nothing action, the group of symmetries of a snowflake includes 12 distinct actions. It even has a fancy name, D6. The simple group of symmetries that only has 2 elements acting on a face also has a fancy name, C2. In general, there is a whole zoo of groups with no shortage of jargon to their names, categorizing the many different ways that something can be symmetric. When we describe these sorts of actions, there's always an implicit structure being preserved. For example, there are 24 rotations that I can apply to a cube that leave it looking the same.
Why is
And those
3B,
24 actions
1B
taken
not a
together
senator?
do indeed constitute a group. But if we
questions.
allow for reflections, which is a kind of way of saying that the orientation of the cube is not part of the structure we intend to preserve, you get a bigger group, with 48 actions in total. If you listen things further and consider the faces to be a little less rigidly attached, maybe free to rotate and get shuffled around, you would get a much larger set of actions. And yes, you could consider these symmetries in the sense that they leave it looking the same, and all of these shuffling, rotating actions do constitute a group, but it's a much bigger and more complicated group. The large size in this group reflects the much looser sense of structure which each action preserves. The loosest sense of structure is if we have a collection of points and you consider any way that you could shuffle them, any permutation, to be a symmetry of those points. Unconstrained by any underlying property that needs to be preserved, these permutation groups can get quite large. Here, it's kind of fun to flash through every possible permutation of 6 objects and see how many there are.